Hello, my name is Ofsibarike John, and my colleague Chiparo Derek. So um, our machine learning project it's titled Contrastive Node Distillation for seed variety classification with capsule network and mechanism attention. So in our project we have some of our keywords. So our first keyword it's um, it's crop varieties. The second one is contrastive node distillation. We have capsule network, mechanism attention, and agriculture. So on our first slide, we have the background and introduction. So in our project, we are using groundnuts as our case study. So that means you have to look at groundnut classification. It's very much crucial, especially in the agriculture sector. So groundnuts they tend to have different varieties, and each variety is suitable in different environment and can be used for different purpose. For example, some can be used for consumption, others can be used for industrial use and such. So there is a big need for farmers to be in position to identify these different varieties of groundnuts. So that may happen to look at the traditional manual method that have been used by farmers to classify these different varieties of groundnuts. These methods are very much less effective. So they are labor intensive, they are time consuming, and they are prone to human errors. Hence, this highlighting a need to automate the process of groundnut classification. So today, machine learning and deep learning techniques such as capsule network, attention mechanism, they offer data-driven solution to improve the efficiency, to improve the accuracy and the efficiency of groundnut classification. So on our next slide, we have our literature review. So under literature review, we are trying to explain or to define some of the technical terms that we are using in our project. So one of the term that our first term that we have is contrastive node distillation. So contrastive node distillation is basically where a large complex model is teaching a student model, basically in how this student model can be positioned to make decisions. So another technical term that we have, it's the capsule network. So capsule network, it preserves the spatial relationship, making them ideal for distinguishing closely related images. And in our case we are using the data set we are using, it's image data set. So another technical term we have, it's attention mechanism. This helps models to focus on key features such as shape, texture, color, etc. Basically this is mainly for better classification. So on our next slide we have our problem statement. So our problem statement is divided into two parts, and the first part is the domain application problem, and another one is the computation problem. So under the domain application problem, this basically is targeting, because our project it's under the domain of agriculture. So farmers are basically facing very many problems in classifying groundnuts. And the existing method that they are using to classify the groundnuts, they are labor intensive, they are efficiency, they are time consuming, and they are prone to errors. So hence to automate the process of groundnut classification. So also on another side, the computation problem. Basically the computation problem, this is on our side, we the people that are going to develop the model, or they're going to develop the machine learning, that are going to develop this machine learning project. So the first problem, we have handling large and complex data. This requires processing high-dimensional features, species, and managing data imbalances. So another problem is ensuring model repeatedness, Another one is computation efficiency, and so so another problem is computation efficiency. So as in the model that we are going to develop must be able to must be able to visualize how to give the results in real time. So on our next slide, we have the research questions and objectives. So the first research question we have: how can the machine learning model be used to accurately classify different groundnut varieties based on the image features? And another one that we have, it's what processing techniques can be applied to improve classification accuracy and reduce computational complexity. So the third one we have, it's how can node distillation and capsule network enhance model efficiency and real-time performance. So the fourth one, it's what impact does automated groundnuts classification have on small farmers productivity and decision making. So the objectives: develop an automated groundnut classification model that this one utilizes machine learning to improve accuracy and efficiency. So integrate advanced deep learning techniques such as capsule network, attention mechanism for better feature extraction. So the next objective we have, it's enhance computation efficiency, optimize this is basically to optimize models for real-time classification on mobile devices and edge devices. So basically this can be in position so that our model can be in position to fit on small devices, and this can and this we are going to be in position to implement it using knowledge distillation, where a teacher model transfers knowledge or teaches a smaller model. So the last objective, it's to support agricultural productivity, basically to improve crop variety selection for increased yield and income. So on our next slide we have the research contributions. So basically the key contributions over what we have been positioned to contribute, or where we are going to be positioned to what we are going to be positioned to our project, what is going to be positioned to contribute on the environment, especially on the side of farmers. So we have developed a machine learning project that's capable to accurately classify different groundnut varieties using image-based features. So we built the first classification framework that integrates capsule network and attention mechanisms to enhance feature extraction. So the next one, we deployed a novel processing pipeline that optimizes image data for improved classification accuracy and reduces computation overhead. So we introduced a lightweight model using knowledge distillation, making real-time classification flexible for mobile and for mobile and edge devices. So we demonstrated the impact of automated groundnut classification in improving agricultural decision, leading to increased productivity and food security. So the methodology, this is like how are you going to be positioned to how are you going to be positioned to implement, where are we going to be, what the steps we are going to take to implement our model from data collection to the model deployment. So our first step in our methodology is data collection, acquire and process images. These images, basically this is the data set that we are going to be in position to use to train our model and such. So the next step, the next process is going to be data processing. So after acquiring the images that we are going to use, we are going to do data processing on it. We are going to do resizing, edge detection, normalizing and such to make sure that our model can be positioned to tell the different variety of seeds, even when given any kind of data image. So the next one is it's future extraction. This we are going to be positioned to implement it using capsule network and attention mechanism. So the next step we are going to do is we are going to do model training, and this one basically we are going to train it using deep learning deep learning techniques such as node distillation and such. So yeah, so the next step we are going to do, we are going to do model evaluation. This we are going to develop a number of models. Then after we do model evaluation and we see which one can be fit, but which one is working well for on our project. So the last step, we are going to do the model deployment, where we are going to be in position to host a model, and it can be in position to be accessed anywhere by farmers or researchers. So so on our next slide, we have the dataset description. The overview. So our dataset was obtained from a private scientist researcher, and it contains about 592 images of different granite varieties collected from from various regions of different parts of the country. So the dataset is structured into subfolders, and these subfolders are named after the seed varieties. So we have our first folder. It's S2T, and the next one it's S3R. We have S4T. We have the S7T. We have the and we have the S90, and each folder contains a number. It contains a number of images that we are going to use to train our model. So the key features of the images in our data set, and these are basically the things that we are going to use to classify the different varieties of granites. So the key features, we have the RGB color composition, we have the texture analysis, we have the structure details, and after this we are going to perform the pre-processing steps. We are going to do normalizing, resizing, data dimension, and such. Yeah. So let me call in my colleague to take you through the next slide.
So on the next slide, we have EDA results, graphs and insights. So first of all, we performed a data analysis on our data set, and we were able to obtain some visuals regarding the data set. So with the visuals we try to analyze the image height distributions within our data set, and this is what we can observe with the image height distribution. So we observe that with some seed images, some have equal height, others are too short, and then others are very they have a higher height compared to the others. So this helps. This one, we did this to find out like the uniformity in the heights of the image sizes, and then some of the other visual that we obtain is the aspect ratio distribution. Like this is plotted with frequency against aspect ratio in terms of width and height, and this is what we obtained here. Then another visual is the distribution of granite varieties, like the image count. Here we are trying to analyze the number of images within our classes. For example, we observe that S4T has about 198 images within it, and then S2T has a number about 180 plus, and then we observe that S3 is having the least number of images within it, and S7 and S9 they are almost equal. They are almost carrying equal number of images of image seeds within them, and then we plotted the box plot of image heights. So this box plot, we were trying to get the outliers in terms of height pixels. So on the next slide we have distribution of image dimensions. With dimensions, we mean we mean the size, the shape, and so on. So this is what we obtain with distribution of image dimensions within our image data set. And then we carried out, and then we obtained the pie chart of ground earth varieties. And this is what we obtained. We observed that S2T is occupying 31.6% of the image data set that we are trying to work with, and then A3R with the least percentage of 2.7%, and then S4T is carrying the largest percentage of 33%. So we did this in order to avoid imbalances within our data set. So we observed that our data set needs to be needs some sort of balancing. So we carried out this to observe that. Then the other one is this one is a continuation of the other one. This is the distribution of ground-earth varieties. This is the image count that I've just explained. And then this is the obtained plot of image heights by variety. And then it's plotted height in pixels against the varieties. On the next slide, so as my colleagues said, we carried out a variety of studies, like we created a variety of models for that, and the aim was to get the one that is suitable, like that can perform better with our data set and the classification task we are doing. So one among the models that we created this 3D mobile net model, we created a distributed vision net, we created a vision transformer that specifically using semantic convolution network, and we created a knowledge distillation sparsity convolution neural network. Then we created a trained distributed vision transformer model, vision transformers. We created the knowledge distillation convolution neural network. We created a semantic convolution neural network that with a sparsity optimization. We created the sparsity knowledge distillation network model, and then the capacitation network model. So on the evaluation of these 10 models based on different metrics, we were able to obtain this table here summarizing the performance of every model in terms of precision, recall, hash race, and F1 score. So in the table we can observe that this 3D mobile net model is outstating, like it's performing best compared to other models, basing on the precision call, the recall hash race, and F1 score perform metrics. So with the mobile net, it was able to achieve an overall hash rate of 98.33%, and then the precision call of 0.98, the recall matrix as 0.98, and F1 score of 0.98. So we So we based on this table to so basing on the table evaluation performance matrix, we were able to observe that the student mobile net model can perform better for our classification tasks, and we based on this to select the distributed mobile net as the model that we are going to use in our classification task. So on the next slide, I have the confusion matrix of the deployed model, because we went further to study the distilled mobile net model that we want to work with in our classification task. And on observation of the confusion matrix, we observed that the model was able to classify correctly because this confusion matrix was done on a test data set containing 60 sample images from the data set, and each subclass was containing 12 images equally. So on observation of this confusion matrix, we observed that the model was able to classify S370, S90, S2T and S3R image samples correctly and perfectly, and it correctly classified the images of S4T 11. It correctly classified the images of S4T. The model was able to classify 11 images of S4T correctly, and it classified the one image of S4T as S90 falsely. Like it misclassified one image of S4T. So this shows that this indicates that there are some features that the models there are some features that exist, like there are some features in common that exist between S4T and S90 classes. So the model struggled to study these features and failed with one misclassification of S4T class and misclassified it as S90 class. Then on the next slide, we have the performance evaluation of the distributed mobile net, and this is the model we are working with. So you can see its performance metrics based on precision, recall, F1 score, and the overall hash rate. It was perfect, and it's very perfect, and it shows, and it gives some promises, like it gives promising solution to the problem of classifying these seed varieties that we are trying to work on. Then on the next slide, I have the conclusions and limitations. So with our distilled mobile net model, it demonstrated disability with reasonable hash rates, as I have shown you. So with this model, we believe that it will help farmers and agricultural stakeholders in different ways. For example, in carrying out decisions, for example, the farmers will use this model, like they will use this model to verify, like to classify which seed belongs to which class, and then the agricultural stakeholders, they will also, and then it will help like researchers, agricultural researchers, and those ones dealing in crops, like those ones that are selling and buying crops. And then with limitation is where you have limited data set, availability and quality. So this is basically our data set. Our data set lacks some information, because we know very well that that some classification is, for example, some classification is can base on the biological makeup of a seed, for example, an embryo. So our data set has no information regarding that, and again, our data set is containing limited number of images. So here we intend to collect more labeled data and improve and including that information that lacks within our data set. And then the other limitation is that we have the other limitation that we have is the class imbalances in the data set, as I showed you on this slide, that S9, the S3R has a list number and has a list percentage of 2.7%, yet other classes are covering 33.3%, 31.6%. So we have imbalances within our data set. Then the other limitation is that we have misclassification. So with the class imbalances in the data set, we can use techniques like data augmentation, oversampling techniques, and so on. Then the other limitation is that there is misclassification due to similar crop futures. So this can be solved with multimodal data, as you can see here. Here the model failed to classify that one image seed of S40 because we assume there are some common features within them. So there is misclassification due to similar crop features. So that is what we had about limitation. So with next steps and the future works recommendation. So with future works, we intend to improve model performance, for example, by by applying more advanced techniques, within our model. We intend to expand the data set by applying those information that is lacking within our data set, collecting more images, and so on. We intend to optimize the model, and then we intend to develop a mobile or a web-based application, for example, where farmers can easily access and classify the varieties, especially in a real-time setting, because where a farmer can just take a snap, scan the image, and then the model tells the farmer that this sort of image, like this sort of crop, falls in this class. So with the recommendation is we have multispectral imaging, for example, for a better feature extraction. We investigate the use of self-supervised learning to handle limited label data sets and explainable AI techniques to improve model interpretability for end users. And then we recommend collaborate with agricultural experts to refine model predictions based on real-world conditions. So that is what we had for you today. Thank you for watching.